Hey everybody, I want to do a little demonstration for Gauss elimination using this really cool new piece of software that was made by people here at the University of Washington. Look up their names again, I got to remember this. Beck Thompson and Edison Howe. I asked them to write it on the website. But let's go over to the website and we'll see how it works. Do share screen. All right. So I think you can see my screen now. I hope so. So the software we want to demonstrate is this linear algebra graphics package. It's on GitHub, and you can access it with this URL, and I'll put it, I already put it in our external resources page on Canvas. So let's do a particular problem with this and see how you can use it. This one that's given, the demo model is really nice, fits in there well. And we want to use it for a problem that we started in class and that we're going to finish tomorrow. But I like this program a lot because it's been helping me when I'm doing the homework. Sometimes I make a small mistake when I'm doing Gauss elimination. And this is one way you can check yourself if you're working all by yourself, or if you have a friend, you can do each step and then compare answers. But here is a problem that we were working on. So let's say you had to solve a system of equations, linear equations, 3 unknowns and 3 different equations. Let's say it was written as 3x plus y plus 7z equals 2. That's the first equation. 4x plus y plus z equals 0, and 2x plus 2y plus 2z equals 2. All right, let's solve that by Gauss elimination. So step 1 is to write down the augmented matrix version. That's where we're going to just keep the coefficients and the constant terms. So the coefficients for the first equation are 3, 1, 1, 7. So that goes into the first row. And remember, with the augmented matrix, we put a line just before the last column. So the coefficient will be 2, and that finishes off row 1. The next equation is going to have coefficients 4, 1, 1, and constant term 0. So that's our second row. Third equation has coefficients 2, 2, 2, and constant term 2. So that becomes our third row. And now the goal of Gauss elimination is to find one matrix that's going to encode a system of linear equations that'll be easier to solve than this. And we'll have, in this case, it'll have triangular form if we're done with Gauss elimination. Okay, so, but in general, you don't, when you do Gauss elimination and you row reduce your matrix, the goal is to always have the leading coefficients going from left to right, but underneath those leading coefficients are always zeros. So we'll end up with like a staircase of all zeros. That's the general form. All right, so remember what we can do. We have 3 easy operations that we can do on matrices that reflect simple things that we can do with equations and maintain the set of solutions to those equations. So we're going to end up with different equations, but with the same solution set. So that translates in terms of matrices into one of 3 operations we can do. And we can do as many of these as we like over and over again, but with the goal of getting zeros underneath the staircase. Okay, so what can we do? We can interchange 2 rows. That's usually denoted something like R1 interchanging with R4, if we're switching 1 and 4. We could multiply 1 row by a non-zero constant. That would be denoted by whatever your constant is. Constant times R1 goes to R1. We're going to replace R1 with this mutated form where we multiply every entry in that row by the same constant. And step 3, we could add a multiple of 1 row to another row. And this is just like saying if A equals B and B equals C, then we also have that A plus C equals B plus D. Something like that. Okay, well, the notation for that will be when we're changing row 2, I like to put row 2 first. And so I'll write row 2 minus 2 times R1, let's say, and we'll put that into the position with R1. All right, So we started off with the augmented matrix 3, 1, 7, 2, 4, 1, 1, 0, 2, 2, 2. And what we're going to do when we want to solve this, of course, you're going to go through the process of Gauss elimination step by step, but I'm going to record it over here on the website. So it's really easy to use. You start off with some numbers that come up the first time you put it in there, but it's easy to tab through and put in the columns. So 3, 4, 2 is the first column. 1, 1, 2 is the second column. I'm just using the tab button to move around. 7, 1, 2, 2, 0, 2. So now I've entered the augmented matrix that I want. I hit return. And on the right-hand side, I'm already seeing the answer. Do you see that? The right-hand side is giving me the reduced row echelon form. So we already did the computation so fast I couldn't keep up with it, right? In the background, the JavaScript has computed the reduced echelon form. And when I read this, what this means is that x is going to be equal to minus 1/3, y is going to be equal to 19 over 18, and z is going to be equal to 5 over 18. Problem's already done in some sense, right? But not exactly, because I was supposed to solve this with row echelon form, and this is just so that I could practice the algorithm. Okay, so the algorithm is implemented in here already. We have 3 different things we could do. We could swap 2 rows. We could, well, we said number 2 was going to be, we could rescale any equation and put it back in the same place, in the same row, or we could combine. This is where we do something like R2 minus 2 times R1 and replace row 2 with that. All right, so what do we want to do first? Well, what we had talked about maybe is taking row 3 in this example and swapping it with row 1. And I'm thinking ahead because I know I want to start having a 1 in the top left position. So let's try that. So we're going to swap R1 with R3. That means the first row with the third row. Apply. And it changed the picture. Did you see that? The hyperplanes have changed a little bit. That's just because it recolored them. One of them swapped. It looks like the blue and the pink ones have swapped. Otherwise, the picture is pretty much the same. All right. Now, I always like to have not just a non-zero term in the upper left, but I like it to be 1. So I'm going to rescale the first row by 1/2. When I click 1/2 times R1, it automatically puts R1 on the right-hand side because it knows I'm doing a scale operation. Once I tell it which row I'm applying it to, it knows where to put it to. It's going to put it in the exact same row. All right, so after that step, you write down the new matrix that you have. This is the new augmented matrix. All right, now back over here on the left, if you're going to be doing this to practice the algorithm, you should be doing it first for yourself and then use the program, okay? So I started to do this. I went step by step. I started with the augmented matrix that I wanted to use to solve the original system of linear equations. And then I did the swap of rows 1 and 3, and I filled it in. And now we could do the same thing. We're going to apply our next step. And I made a little worksheet for us so that I don't have to put in the boxes every single time. I just started to fill it out. And my next step, after I rescaled row 1, so the first row is going to end up being 1, 1, 1, 1. Then I'm going to, what am I going to do here? So I want to, underneath the upper left-hand one, I would like to use row 1 to zero out all of the entries that are directly below that upper left one. So what do I have to multiply? What do I have to do? I want to take R2 and subtract 4 times R1 so that it works out. So I'll end up with a 4 minus 4 in the first position, and I'll get a 0. Okay, so over here, I have to tell it, I'm going to combine rows. I'm trying to fix R2, so put that in first. I'm going to subtract 4 times R1. And it automatically knows that I'm going to put that in R2. So it starts out with R2 and it knows it's going to fix R2 that way. It's going to only change row 2 when I do this. There we go. And did you notice the hyperplanes changed? It shifted the position. It tilted one of these hyperplanes a little bit, but it's still around that pivot point, which is their solution, which is the one point in the middle. So it's just tilting around the existing solutions. Great. Okay, so this is a little bit better, a little bit closer to echelon form, but I have to continue to put a 0 everywhere in the first column below that, the 1. Okay, so I'm going to combine again, and this is now fixing row 3, and I'm going to subtract this time 3 times row 1, and I'm going to put that in row 3. There we go. Tilted the plane again. It tilted the R3 plane a little bit more. All right. Not quite done. We have, now that we need to fix up the bottom 2 rows. First column is done. Let's fix up the second column. Okay, so, well, what can we do? We have a choice. We could swap, we could combine, or we could scale. I'm going to choose to scale. I'm going to choose to rescale the second row by minus 1/3, because then I'm going to end up with another 1 in position 2, 2. And well, it's just easier for me to multiply. So when I went to fill in the table for myself, I thought it was easier to put another 1 there. All right, now that I've got a 1 there, well, I said I could either use that 1 in the position 2, 2 to clear out the next row, or I could actually rescale the next row to make it easier for myself when I want to do the combination. So when I was doing it by hand, I also said, let's divide by minus 1/2. And we're going to do that to row 3. Apply. That's just a choice. I didn't have to do it that way. I didn't have to make that step, but I did so that I ended up with 1, 1, 1 in the first column. That's not the end goal, but it just made it nice. Okay. So where are we here? Let's just check. I'm doing the computations first by hand, then I'm checking on the computer, but you're seeing in the other direction. All right, so it looks to me like we are here on this page, keeping track for yourself. And now, what are we going to do next? Well, we have a leading 1 in position 1, 1. Well, in row 2, the leading term is in the second column, and we're going to use that one to clear out all of the things that hypothetically would be below it. So there's only 1. It's not hard to do this. We're going to do 1 more combination. And so we're going to fix row 3 by subtracting how many of row 2? Well, I only need 1 at this point. All right, so I put in R3 minus 1 times R2 and replace R3 with the combination. So there we go. We have a new matrix. It's an augmented matrix. It's 1, 1, 1, 1 across the top, and then 0, 1, 1, 4/3, 0, 0, minus 3, minus 5/6. So the top row never changed after I rescaled it. Okay, well, this is great because now we have leading terms in the first row in column 1, leading term of the second row is in column 2, leading term in the third row is in column 3. Those are all different. They're all progressing from left to right. There are zeros underneath every one of those leading terms. And so voila, we have the echelon form for our augmented matrix. It's exactly the same echelon form if it wasn't an augmented matrix and it was just a 3x4 matrix. It's the exact same echelon form. All right, and take a look at the planes. Those are the 3 planes that intersect at the exact same point. But in order to figure out where exactly is that point, we would still have to solve these equations. For example, we'd say minus 3 times z is equal to minus 5/6. Well, okay, move the minus 3 to the other side. That would mean z is equal to 5/18, right? And that's coming up here in the reduced echelon form too. We're seeing that. So, okay, so it's easy enough to solve for z, and then we would have to plug that in to the equation corresponding to what the second row, which is y plus z equals 4/3. And then we solve for y. It's going to be 19 over 18. I can see that already. But we would like to, let's just go ahead, instead of stopping with the echelon form, let's go all the way through and get the reduced echelon form, which makes it super easy to solve. So in terms of what I'm doing here, the steps on this lovely program that was made by Beck, Thompson, and Edison Howe, we're just going step by step until we get to the reduced echelon form. Okay, so let's keep going. What do we have to do to get to reduced echelon form? Well, one thing I see is we need to rescale that bottom row. So rescale it by 1/3. R3, it's going to go to R3. And voila, now we have the rescaled version. We already talked about that. Now we're going to use the leading ones, not just to clear out the non-zero things below, but also to clear out the non-zero things above. We can add lower rows to upper rows just as well as we did before in combinations. So we can combine. Well, how are we going to do this? Let's take, first of all, row 1 and subtract from it 1 times row 2. Now I'm looking ahead and I'm seeing, okay, this is going to work out really nicely because in row 2 I have 0, 1, 1. When I take that away from 1, 1, 1, 1, well, I'm going to get zeros in 2 places, right? I'm going to zero out the position 1, 2 and the position 1, 3. And okay, I had to also subtract 4/3 minus 1, which is minus 1/3. So that's easy enough to see. Let's follow along. I hope you're doing the table here on your own. All right, so now we've cleared out the top row. We've cleared out what we can in the top row. We have 2 zeros here after the leading one. So let's fix up row 2. So in row 2, we can combine, and we're going to take R2, and we're going to subtract from it 1 copy of R3. And when we do that, we'll have the leading term is 1, but then everything to its right, well, not everything to its right. Everything above the leading term in row 3 will end up being 0. There we go. And that's it. Those are the 10 steps to get to the reduced echelon form. It exactly agrees with what the program had produced in the beginning. Here it is. We're happy to see it because now we know how to solve our original problem. But before I go back to the problem, take a look at this. I'm going to spin the hyperplanes around. What's special about these hyperplanes now? They're orthogonal. It's really cool. What we did was we started with 3 planes which are kind of at skew angles to each other. And in the process of moving to the reduced row echelon form, it perfectly makes sense that now we ended up with 3 orthogonal planes because this is like x equals minus 1/3. Y, that's I guess the blue one here. And then y equals minus 19 over 18. Well, that's orthogonal to a plane parallel to the x-plane. And then z is equal to 5/18. Spin it around. Very cool. Now here's one of the buttons that I think is so fabulous on this program. It's the animate steps down at the bottom. Right now we plugged in all of these 10 steps that we did little by little, making incrementally small changes to the system of equations while always preserving the solution set. And we did it in such a way that we, first of all, found the leading term in each row and zeroed out all of the non-zero entries below it. Then on the second row, we found the leading term and zeroed out everything below it. Then on the third row, we turned it into a 1. And then we used that leading term, which is a 1, to clear out all the non-zero things above as well. Okay, so that's how we got all 10 steps are still sitting here. And you can watch this in animation on the hyperplanes. Original, and now they're moving into orthogonal position. little by little in each of our 10 steps. Well, voila, they're done. Okay, so that helped us find the solution. And once we have the reduced row echelon form, translate that back into what that means in equation land. Okay, that encodes a linear equation, 3 variables, 3 unknowns. So there is our augmented matrix. It doesn't matter if, while I was row reducing, if I had this extra bar here or not. It didn't mean anything for the algorithm that we were doing in terms of Gauss elimination. But once we have the augmented matrix, once we finish our Gauss elimination, we put the bar back in and we interpret that augmented matrix as a linear equation. So x equals -1/3, y equals 19/18, z equals 5/8, which is super easy to solve. So the solution set, in this case, is 1 point, and it's living in 3-dimensional space because there are 3 unknowns. So -1/3, comma 19/18, comma 5/18. That is that point of intersection of the hyperplanes, right around there. So hopefully you can see it and understand the process. Thanks for listening.